Hi, everyone. So as you heard, I'm Aaron, and today I'm going to tell you about my research on looking for spin liquids with computational approaches. So the first question which you might ask is, what are spin liquids? And to answer that, maybe the first question is, what is spin? And so we know that electrons are particles which have various properties, such as mass and charge, and it turns out they also have what we call a magnetic moment. And that means that every electron acts as a small magnet, and this is what we refer to as electron spin. And we illustrate it, as I've shown here, by a little arrow indicating like a sort of small bar magnet with a north pole and a south pole and so forth. Okay, so that's spin, and now I think we know what a liquid is. Like, here's some liquid in my water bottle. So maybe a spin liquid looks like this. We take some spins and we put them in some liquid, and that's a spin liquid. Well, it's not so simple as that. So we actually need to ask as well, what is a liquid? All right, so imagine that we have, let's say, water again, and it can be in a liquid or a solid form. And the difference between these is that in a solid, we have this rigid crystal structure where all of the water molecules are in fixed locations and with fixed rotations. On the other hand, in liquid water, we actually have the water molecules at random locations and with random rotations. So we can have an analogy for these electron spins where the so-called solid version, the electrons form this rigid structure. They're all located at fixed locations, let's say in this square grid as I've shown here, and their spins all point in the same direction. They all point up in this picture. And this is what we call magnetism. On the other hand, we could have a so-called liquid of spins. The electrons are still fixed in all the same positions, but now just the directions of the spins point in randomly. And that should be true even if we go down to very low temperatures. So this is the kind of thing we're going to be looking for, these spin liquids. Okay, so do these things actually exist? Well, of course, this is the question we want to answer. But you might think, based on going to the archive and searching for a spin liquid, and you find that there's 3,000 results, so people have been studying this a lot. Probably people wouldn't be studying it if they didn't exist. That's what you would think. But actually, the answer is they probably exist, but we aren't actually 100% sure. So why is that? Well, there's a couple of challenges. So one is that experimental results can be in some ways ambiguous, and then to try to clarify what the experiments are telling us, we need to do some theory work. And then it turns out that theoretical models are really hard to solve. And a combination of these two things means that we've been looking for spin liquids for 50 years without actually finding one definitively yet. So today I'm going to tell you about why these theoretical models are hard to solve and some possible solutions. So the goal of doing theory is that we can resolve some ambiguity in experiments. And what that ambiguity looks like could be we have a spin liquid. I'm still using this picture even though it's wrong, but I think it's quite evocative, versus some other kinds of states. So the one I'm showing here is called the valence bond solid. That doesn't really matter, but the point is it's something else which can kind of trick you into thinking it's a spin liquid, but it's not. So both of them have no magnetism at low temperatures. They have high entropy at low temperatures, and it's not that clear from an experimental perspective how we can distinguish them. So to answer this, we go to theory, and we follow this procedure. We start with our real material. We try to make a simplified model of it. Then we try to solve that model and ask whether we got a spin liquid or not, and then we ask what are the experimental signatures. And there's a lot of challenges here. So it's hard to make a model which is both simple enough to solve and to get some conceptual understanding out of it, but still realistic enough to actually capture what's going on in the material. Then it's really hard to solve that model due to quantum entanglement. And finally, even if you can solve the model, translating that into a real material which has some defects and imperfections is going to be quite challenging. So today's talk, I'm just going to focus in this middle part on the challenge of solving the model, and in particular, the challenge of quantum entanglement. So to understand quantum entanglement, the real problem is that it produces exponential costs for computer simulations, and we can understand this by looking at spins, both classical and quantum. So we start with just looking at one spin. You can imagine that basically what we need to know is the direction that this little magnet points, which is specified by our two angles in spherical coordinates, theta and phi. The quantum version of this is that we have what's called superposition of a spin can be pointing up or a spin can be pointing down, or we can have a sum of those two with different coefficients, again given by two angles. So in some sense, a classical spin and a quantum spin are both given by two parameters, so they're kind of equivalent with each other. On the other hand, we can go to two spins, it starts to get more complicated. So in the classical case, we can just describe our two spins independently. In the quantum case, we could try to do the same thing, and that's what we call a product state. But states more generally are given as what we call this full superposition of four different states where the spins can be in all combinations of up and down. And it looks like we have four parameters still on both sides, so it's not clear that there's anything new going on, but it'll become more obvious when we go to more spins. So we have three spins now, and on the classical side, we again describe them all separately. On the quantum side, our superposition now has 8 different terms, so now we have 8 parameters on the quantum side, 6 parameters on the classical side, and that means that there's more states on the right than on the left. And so the new states we refer to as entangled. And this is going to cause a big problem computationally when we go not to 3 spins, but to many spins, which we'll say n. In the classical case, we have to describe this with 2n parameters, but in the quantum case, it requires an exponential number of parameters, which makes the problem very hard. Okay, so what's the solution? So a classical solution is to use what we call tensor networks, which efficiently capture this quantum entanglement. So we have a spectrum of states going from these product states, which are kind of classical-like with not very many parameters, up to our full entangled general states. And the product states are really easy to work with, but you often get the wrong answer because they're not very general. The general states, of course, always include the state you're looking for, but it's almost impossible to do anything with these. But we can get the best of both worlds using what we call tensor networks. In particular, something called a matrix product state, which I'll denote with this little picture, which you don't need to understand, but that's a little symbol, which you'd think of. That means I'm using tensor networks here. What you do need to know is that tensor networks work with a parameter, which we call the bond dimension, which tunes between these limits of when bond dimension is small, you have this product state with very low precision, but also very fast calculations, and you can tune this as much as you want up towards high precision and slow calculations. So I've used this method successfully to find a spin liquid in a challenging theoretical model, which I'm going to tell you about is in this paper here. So we look at a particular real material. It's this complicated organic crystal, which is the first material that was claimed in experiment to be a possible spin liquid back in 2003. And we're going to model this as a grid of triangles, and there's on average 1 electron on every side of this grid. And the electrons interact with each other. There's an interaction we call U, which says electrons are not allowed to be near each other. There's an interaction we call T, which says that electrons can move easily and freely and move past each other. And now we're going to solve this model using tensor networks. And so we solve it as a function of this parameter, U over T. So in other words, the ratio of basically how freely the electrons can move. And the result of the calculation is that there are 3 different phases of matter you find as a function of this ratio U over T. When the electrons are really constrained and can't move, we actually get a magnet. When the electrons can move very freely, we get a metal. And in some intermediate regime, we find one of these spin liquid phases. Okay, so this was a classical solution. It turns out we have another solution, potentially using quantum computing. So here, we can actually try to solve the same entanglement problem by going directly to quantum computers where entanglement is natural. So in this case, because these fully general states, they were hard because they have quantum entanglement, but on a quantum computer, you already have quantum entanglement for free. Free given that you have a quantum computer. Okay, but it's not just, that's not the only cost. There's additional challenges that come up. So one challenge is what we call unitarity, that if you want to make transformations on your states, you can do things that are like rotations, but you can't do things that are like squishing your states. Another challenge is measurement, that if the state you want to find that you have is sort of this one at 45 degrees, then when you make a measurement, you'll either get this one or this one. You won't actually get the original one, so you have to do it many, many, many times and take some statistics. That's another difficulty. And then finally, there's a lot of errors. So we have this bit flip error, the kind that you can have in classical computing. We also have a new type of error called a phase flip, and this can happen more easily than in classical systems. Okay, so I'm going to tell you a bit about how we can address this challenge of unitarity. So one key idea is to use what we call hybrid quantum classical algorithms, where we're going to use some features of the quantum computer to deal with the difficult entanglement aspects, but a classical computer to deal with the fact that we can't do these unitary transformations. In particular, we're going to use something called the Krylov subspace method in order to find the smallest eigenvalue of a non-unitary operator, which could be like your energy function, your Hamiltonian for your system. So we start with our quantum computer. This is a picture of the Honeywell/Quantinuum ion trap computer. And here we're going to make some bunch of unitary measurements and unitary operations. And when we do that, we generate a list of states. We start with some initial state, we rotate it, we got a new state, we rotate it again, we got a new state, and we can keep doing this and generate a whole bunch of states that are rotated. Then I put these states and I evaluate my operator in that basis, and I get what's called a generalized eigenvalue problem, which I then solve on my classical computer, which you can see here. So I solve this generalized eigenvalue problem, and possibly we can get a spin liquid this way, solving a model, and that is coming soon. This is in progress now. To finish, I want to acknowledge my collaborators. The published work which I showed you was done with Johannes at University of Geneva and Mike Zalatel and Joel Moore, who are at UC Berkeley. And then the quantum work is in progress with many folks here at the lab who I've listed here. And with that, I will put up my summary and take your questions. Thanks very much.
Do we have questions from the audience? Don't be afraid.
Yes.
So I'm very sorry if this is a bad question. Please don't hate me. I'm not a physicist. Why do we want to find these spin liquids?
Yes, so I had a slide about this, but I took it out because it was out of time. But it turns out that one of the reasons is actually we're building a quantum computer. So, of course, we have, I showed this picture of an ion trap quantum computer, and we also hear a lot about superconducting qubits. But all of these things are very prone to errors. And there's a different idea called topological quantum computing, where you would use what's called topological phases of matter to generate a qubit which doesn't interact with its environment very much, except when you control it, and therefore should be very long-lived and can have gates with no errors and that kind of thing. And it turns out that spin liquids are topological phases and could be used for this purpose.
As we know, the tensor chain, the matrix product state is just one compressed format for possible compressed format for the large matrices. So do you think other compressed format could also help us to solve this problem classically?
So in my opinion, these tensor networks in general, not necessarily matrix product state specifically, which is sort of a one-dimensional tensor network, but tensor networks in general, I think, are the best classical framework because they're explicitly designed so that when you make an approximation, what you're doing is you're cutting out like small bits of entanglement, and you're leaving the most important entanglement in the system. And there's controllable ways of doing that in your algorithms. So it captures the most important features of your quantum states, and especially for finding low energy states in realistic systems, there's some theoretical results in something called the area law, which basically says that tensor networks are going to give you the best possible approximation.
All right, if we have more questions, we can talk to Aaron during the break. Let's thank our speaker once again.